This video here is one of the most fundamental relations in all of electronics, and it's called Ohm's law. So if you want to know the importance of this law, when you think about mechanics and physics, everyone often walks around muttering F equals to ma. So this might be the mother of all of mechanics. Well, Ohm's law here, which I'm about to tell you about, is definitely the mother of all electronics. So if you watch a previous video and you're starting to get yourself a little bit more educated on electronics and stuff, you must realize that volts, current, and resistance, which are the three primary electrical parameters here, they're not the same thing. They're all different. They all play a different role. And if you watch the last video we had on VI and R, volts are like the pressure or the pump. I is like the flow of electrons or water. And R is like the obstructions or the machines that the water tries to get to turn, or alternatively the machines that the electrons travel through. And there's a definite relation between them, and here it is. This is Ohm's law. It turns out that Ohm's law states that voltage at any given time is equal to current times voltage. As we go through electronics now, you may have seen this before, you may think, well, everyone knows this and stuff, but it turns out that this form of Ohm's law, although true, really isn't maybe the best one to remember, or isn't the best one that gives you the most intuitive feeling. So we're not going to use it all that much here. Instead, we'll always just sort of do a quick algebraic manipulation in our head and say instead that current is equal to volts divided by resistance. This is the one here that's sort of much more suitable for some intuitive feeling about what Ohm's law sort of tells you about how an electrical system works. So I is V over R instead of V equals IR. And let's see if I can give you a few examples about how that works or where it comes from. So what it allows you to do then is if you can sort of believe that about Ohm's law here, or maybe start to remember here that I is equal to V over R. So what it tells you then is it tells you like how much current you would expect to flow through a system given two things. One, given how much voltage is trying to cause the current to flow, that's V, and how much resistance the flow is encountering as it goes. So it looks something like this. Suppose we have a resistor here, and I'll just sort of draw the resistor like this box here like this, although in another video when we introduce electric circuits here, we'll see that resistors have a symbol like a zigzag like this, indicating a very difficult path for electrons to travel through. That's a symbol for resistance, but for now we'll just keep it like a little box. So what you have to imagine that as electrons travel through this box, they encounter a heck of a lot of resistance and impedance to their flow. So the question then, if you have this much resistance sitting here, how much current can possibly flow through this thing, given that maybe I connect it to, let's just say, a 9-volt battery, something like that. Okay? And commonly now, so this would be a 9-volt battery I'm trying to drive it with, values of resistance can be just about anything from 1 to 2 ohms all the way up to mega ohms, millions of ohms if you want. We'll just choose one with some simple numbers here. Let's just maybe choose something here, like suppose this is a 2 ohm resistor. It'll make some mental math easier in just a second here. So we're trying to connect a 9-volt battery across something that has 2 ohms of resistance. So the question is, how much current is going to flow down through this resistor? How much current is going to come out of the battery here, flow out of this positive terminal, around the loop here, through the resistor, and back around to the battery? What is that current going to be? So you can clearly see then that voltage, current, and resistance just aren't the same thing, because the 9 volts sits here on the battery. The current is what actually flows through the loop, and the resistance, of course, the impedance that the current encounters on its way through the loop. So if you wonder how much current is going to go through this thing, it's a pretty simple application of Ohm's law here. It just says that current is the voltage, 9 volts, because this resistor, because it's connected directly across the battery, has 9 volts across it. So 9 volts divided by 2 ohms like that, and that gives you 4.5, and then the units of current are in amps. Amperes also has just the simple A, or sometimes it's called amps like that. So that's sort of the situation. You get 4.5 amps flowing through it. So then the question becomes, well, what if I half the voltage down to 4 volts? Well, you can use Ohm's law again to get that current. You get 4 volts divided by 2 ohms. And that's just 2 amps of current going through there. And you might say, oh, okay, well, wait a minute. Let's go back to the first case here. Let me keep that current, or that voltage rather, at 9 volts, like that. Let me cut the resistance. Let me make the resistance a little higher. Let me make it maybe 4 ohms like that. Instead of 2 ohms, I'll double it. Make it 4 ohms like that. Well, you just sort of keep going here. 9 volts divided by 4 ohms, something like that, is going to be 2.5 amps. Something like that. So that's sort of the nature of Ohm's law there, is I like to look at it as sort of something that gives you a bit of cause and effect. So that the cause over here is definitely this side over here. The cause is definitely because you have a voltage, and the cause is definitely because you have some resistance around. And the effect over here is the I over here. This is the effect. You get a current flow, And how much current flow, of course, depends on the cause side of it. It depends on how much voltage you put across a particular component and how much resistance that component has. And that's sort of the name of the game there. So I is V over R is Ohm's law. It's going to come up a lot more, but it's just the rule of thumb that you can sort of walk around with to sort of understand exactly how much current flow, the effect you're going to get in an electrical device, given that so many volts and ohms were other properties that were in existence around that device at the time.